let's take a look at the homework that I assigned a couple of lessons ago now. And that was page 170, questions 1, 2, 7, 9, and 10. Question number 1, you want to read it for us and give us the answer, Audrey?
What is the definition of work? What is the basic work equation? The definition of work is the transfer of energy from one body to another, and the basic work equation is W equals FD.
Excellent job. Number 2, what are the units of work in the SI and US customary system? Kendall?
The units of work in the SI is joule, and the US customary is foot pound.
Excellent. Number 7, state the definition of average power both in words and in an equation, Michael.
The definition of average power is the time rate of doing work. Its equation is P equals W over T.
Excellent. Number 9, what are the 3 major units of power, Audrey?
The 3 major units of power are watt, horsepower, and foot-pound per second.
Excellent. Number 10, what did horsepower originally mean, and what's the conversion between horsepower and the SI unit of power, Kendall?
Horsepower originally meant that horses were used to move heavy loads like wagons, and the conversion between horsepower and the SI is 1 horsepower is approximately equal to 746 watts.
Good. And so it was when James Watt was inventing the steam engine, he was trying to show, okay, how powerful is this thing? Well, it can do the work of X many horses, so he kind of came up with that. More a contrived thing than anything. We'll get into that a little bit more in our next lesson. All right, so next thing in your notes, we are going to discuss that 4-letter word that frightens so many teenagers, work. In the hallway just a moment ago, I heard one of the teenagers complaining about all the work going on in tests and quizzes and studying and all this work, as if millions of people hadn't done the exact same thing for the last 50 years. But, again, it's stress. Stress hits us all, okay? But work, we're not talking about that kind of work. We're talking about work in this sense. If you would write this in your notes, work is the transfer of energy from one body to another. Now that's in the book. I'm going to add a little bit more to this. Transfer of energy from one body to another as evidenced by motion. The transfer of energy from one object to another as evidenced by motion. This calculator sitting here has no energy. It's just sitting there doing nothing. All of a sudden, watch, it's moving. It has energy because it's moving, so you know it has energy. Where is it getting this energy from, class? Me. I have done work. I have moved the calculator. Okay? So when something moves, it got its energy from something. The energy was transferred. That's work that has been done. So for work to be done, motion must take place. Otherwise, no work. For instance, heavy weights on the floor. Come up, get underneath it. Oh. And if it doesn't budge, I may have popped a blood vessel, but I haven't done any work. Work requires something to move. Okay? Now, if we think about motion, right? If I move something a lot, does that not imply or suggest that there has been a lot of energy transferred? Right? For instance, if this water bottle just slides a little bit, okay, that's a little bit of work done. I transferred a little bit of my energy to make it slide. But if it flies all the way over there to Michael, good catch, then it's done more work because it went further, and Michael can do work here. And all of a sudden, this water bottle has all kinds of energy. Oh, now it doesn't. It's just sitting there now. But it had energy for a moment, right? Where did it get the energy from? From me and then from Michael. We transferred our energy. And if we chucked it all the way back at Audrey, just kidding, she's not that much further anyway, but the further it goes, right, the more energy must have been transferred, therefore the more work must have been done. Does that make sense? So we would say then that work is proportional to displacement. Work must be proportional to displacement. Greater displacement is evidence of greater energy transfer, therefore evidence of greater work done. But if I chuck this water bottle over to Michael versus this lab stool, if I chuck the lab stool to, I'm not actually going to do it, but it's not a bad idea. All right, just kidding. If I chuck the lab stool over to Michael, same chuckage, right? Same displacement, but to get lab stool over there would require greater force, right? Put more force into it. Why? Because it has more mass, right? Same displacement would require a greater amount of force, though, so still greater work done. If I just toss this over to Michael, all right, that took virtually no force at all. Just hit the lab stool. All right. Anyway, but virtually no force required, even though this displacement is a much less work done. So we also understand that work is proportional to force. Well, if that's true, if work depends on those two things, displacement and force, we could say, therefore, that work equals the product of force and displacement. Work equals force times displacement. Now, we know that force class is measured in newtons. And we know that displacement is measured in meters. So work is measured in newtons times meters. But just remember kilograms times meters per second squared. It just gets complicated. So we said, well, we'll call that combination of units newtons. And if we had newtons per meter squared, well, we're going to call that combination of units pascals. We're going to give this a name. And we're going to say that 1 newton per meter is 1 joule. Abbreviated capital J. Named after James Prescott Joule. It actually has nothing whatsoever to do with amethysts and diamonds and rubies and such, but it's a joule, Joule. Now, you can remember this, ladies, because if your husband is a hard worker and he makes lots of money, he can afford to buy you joules one day. And if he's a lazy, good-for-nothing slob, then you're not getting no joules, right? So if you want to remember it that way, work equals joules. Okay, maybe that'll help. And then, and from your perspective, Michael, if you go to work, you can afford to give her joules and keep happy wife, happy life, and all of that. Or hopefully marry a woman who's not so shallow to need things like expensive joules. Anyway, that's in the SI. In the US, we go with, force measured in the US. We measure force by pounds, and we would measure displacement in feet.
Yeah.
So we'll say foot-pound. And we don't have cool units in the US because we're lazy. We don't want to come up with stuff like that. And we don't have a lot of great scientists we want to name stuff after. So we'll just say foot-pounds. All right, so we have in the SI class, we have joules of work. And in the US, we have foot-pounds of work. Now, there is one important concept on the force that we need to note. The force that causes the motion is the force to which work is proportional. Work is proportional to force, or at least it is proportional to the component of force that is in the direction of motion. For these to work together, force and displacement, they must be collinear. If I apply force in this particular direction and the motion happens in that direction, then their product is the work done. But for instance, let's suppose I push this thing across the room. Well, am I pushing horizontally? A little bit, yes, but perfectly horizontal would be to get behind it and push horizontal, correct? Now all my force is in the direction of motion. When I'm pushing this way, I'm pushing down and I'm pushing forward. It's not the actual applied force that causes the motion, it's only the forward component of force causing motion. If I pull back this way, I'm lifting up and I'm pulling backward. Well, the lifting up isn't causing the motion because the motion isn't upward. The motion is backward. So only the component that is backward is the component that we would contribute to the force here. So it's not actually applied force, but the applied force component that causes the motion or is in the direction of motion. Questions on that? And we'll get to some interesting implications of that as well. Now, another thing that's kind of interesting is, by definition, a product of vectors always produces a scalar quantity. Well, force is a vector, and displacement is a vector. Write this in your notes. Work, then, is a scalar quantity. Work is a scalar quantity. How so? Well, imagine for a moment that I drag the lab stool across the floor. Okay? It took work to move the lab stool across the floor, correct? And then suppose I drag it this way, back to where it had been. I did work to get it that way. Force was in the direction of motion. That was work. I dragged it back this way. That was more work. If work were a vector, then returning it to its original position is a net displacement of 0. That's not how it works. I did work there, and I also did work back. We would add the two works together to get more work, not 0 work. Okay? Now, I say that, you're gonna get confused in a minute, but for now, just know work is a scalar quantity. So that we're looking at total distance, if you will, traveled, rather than just the net distance. So for instance, if a student were to go out to the PE field and were to push something all around the PE field and return to the original position, that's not 0 work. We would actually end up taking the total distance, if you will, that was traveled, not necessarily per se displacement. And yet that kind of comes in just a minute with something else we'll talk about. Okay, but for now, just know it's a scalar quantity. Let's look at a couple problems, and then I'm going to give you some implications that are going to make it sound like work is a vector again. All right, but let's go look at example 11.1 there on page 159. Page 159. And read that problem for us, if you would, Kendall.
A man pushes a 100-kilogram crate 28 meters across a horizontal floor at a constant speed. If the coefficient of kinetic friction is 0.65, how much work is done on the crate?
All right. So here we want a free body diagram, right? We have this crate. It's a 100-kilogram crate. And it's being pushed across the floor this way. There is an applied force, a horizontal force pushing it. However, that's not the only force acting on the box, class. What other forces are in play here?
Right.
There's weight that acts straight downward.
Normal.
Normal force that supports it from falling through the floor.
Friction.
And normal force produces friction force, which if we're going that way with the box, friction force would go the opposite direction. First of all, how much would the box weigh? 980 multiplied by 9.8, 980 newtons. Which means if everything else is horizontal, the floor is supporting all of that, the normal force must also be 980 newtons. And we can take that normal force multiplied by the coefficient. This is a pretty rough crate and or pretty rough floor. We get a 0.65 coefficient of friction. That's pretty big.
637.
Exactly?
Yes.
All right, that works out great. 637 newtons of friction force. Now, it says the man moves the crate across the floor at a constant speed. If it's moving at a constant speed, class, then there is no acceleration, which means the sum of the forces is 0, meaning they all cancel out. So if there's 637 newtons of friction force, the applied force must be 637 newtons. Now, that's important because although the box weighs 980 newtons, the man is not applying 980 newtons of force. That would be if he tried to lift the box, correct? Then it would be 980 newtons of force. If he, I don't know, maybe he had a pulley system or something, you know, and he pull, and the box comes up 20 meters. We'd be applying a force of 980 newtons over a distance of 20 meters vertically, right? And that would give us his work done, force times displacement. But instead, the work done is this force times the displacement of 20 meters. Does that make sense? So free body diagrams are not gone. We'll still use them as needed, and we'll use it here, and we'll find how much work was done. 12,740, and let's see, round it off to 2 sig figs, 0.65, good call. 13,000 joules, or we could say 13 kilojoules. We could say 13,000 joules. We could say 1.3 E4 joules. Any of those would work. I'm partial to 13 kilojoules just because I'm lazy. But anyway, there we go. All right, questions on that problem? All right, pretty straightforward equation. Work equals class?
Force times.
Force times displacement. But again, it's the component of force that's in the direction of motion. Let's look at an angled force now. Turn over to page 160. Page 160. And read example 11.2 now, if you would, Audrey.
A girl is pulling a sled that is accelerating at a rate of 5 meters per second squared. Neglect the friction between sled runners and snow. The rope of the sled is 5 kilograms and the angle between the rope and the sled is 30 degrees. A. How much tension force is in the rope? B. How much work is the girl doing on the sled when she pulls it 2 meters?
Alright, so we have a sled. How should I draw it? Box. Do this with me. There are 2 seats. There's the sled. And it tells me the mass of the sled.
5 kilograms.
5 kilograms. And she's pulling it by a rope. So there is rope here that has tension force. Or we could say that's the applied force, correct? Because if she weren't pulling on it, there would be no tension. Right? If the rope were just sitting there, no tension. It's got tension because she's applying a force to it. All right, so there's the applied force. And it says it's at an angle of 30 degrees. So, is she pulling up or is she pulling forward, class?
Yes.
Yes. She is pulling forward. That's the applied force or tension in the X. And she is lifting up or pulling up. That's the applied force in the Y. Now, here's the question. Which direction is the sled moving, up or forward? Only forward. She's pulling up and forward, but it's only moving forward. So the only component that affects work, class, is
Yes.
the applied force in the X. The work she is going to do will be the applied force in the X times that displacement. Does that make sense? Now that's for part 2 for finding the work. All right, what other forces are in play?
Weight.
We have weight, which acts
Down.
straight downward. We also have, will the normal force equal the weight?
No.
Not this time, because the normal force has some help, doesn't it? The normal force isn't doing all the lifting. Normal force is working with the applied in the Y to balance out the weight. Now we can calculate the weight very easily.
49.
Yeah, 5 times the 9.8 comes out to 49 newtons of weight. All right, so between the normal and the applied in the Y, that's going to add up to 49 newtons. And where there is normal force, there is also friction force, which is going to act opposite the motion. Now, once I know the normal force, I'll find the friction force. But I know this. I know how far the girl moves the sled. She moves the sled, class, 2 meters in this problem. I don't know the applied force in the X. I know the mass. And right at the very beginning, class, it tells me,
Don't worry about friction.
oh, neglect friction. Well, if I can neglect friction, then I can also neglect normal force. Yes, I mean, not that they don't exist, but I don't have to worry about them if it's saying to ignore friction. Well, that makes it easy. What else do they give me right off the bat?
Acceleration.
They give me an acceleration. The acceleration says is 5 meters per second squared. Well, if there's acceleration, class, it means that one of the forces is winning, right? Which, of course, the applied force in the X is winning. There is no friction to resist it, okay? So whatever the applied force in the X is single-handedly causing all this acceleration. How do I normally find acceleration? Sum of the forces in the X over the mass, right? Therefore, the sum of the forces in the X would equal mass times acceleration. Well, the mass is 5, the acceleration is 5. What is the net force, the resultant force in the X class? Apparently 25 newtons. But there's only one force in the X. What's the only force in the X class? Applied force. We said friction's gone. Even if there were friction, she would win by 25. Apparently the applied force in the X is 25 newtons. I could actually find the second part of this first. What's the work done? 50 joules. And is it 2 sig figs, I hope?
Yes. No,
3. 50.0 joules it is. All right. 50.0 joules of work done. Well, that's the second part, though. The first part is, how much tension is here? Well, if I know this number right here is 25, then if I wanted to, I could find this side of the right triangle. But I don't care, because I don't care about normal force or friction force. But I do need to know this. And in my right triangle, this line right here, class, is the hypotenuse. This is the adjacent. What trig function? Cosine. So TOA, cosine is adjacent over hypotenuse. So we can say that the cosine of my 30-degree angle is equal to the adjacent 25 over the hypotenuse, which is the tension or applied force. But how do I get that tension or applied force by itself? Alternate. So we're going to take 25 divided by the cosine of the 30. And apparently, how much applied force does she use? Or rounded off, you said it was 3 sig figs, so 28.9 newtons. But again, that's not the force that causes the motion entirely, right? So even we're not going to take this force times displacement, just that force times displacement. And so there's our two answers. It's all kind of backwards, reverse order, but questions on that. A good review of free body diagrams as well. So here's 3 implications I want you to get in your notes. 3 implications of this whole force component that's in the direction of motion. 3 things I want you to get down. That since only the component of force that is in the direction of motion actually affects work done. On Monday, we will be, some of us will be picking up a whole lot of boxes. And some of the boxes we'll end up moving all the boxes to that downstairs hallway, and we'll be picking up a box of food and carrying it out to the truck, right? Now, when you bend down, lifting with your knees, not with your back, right? And you pick up the box of food, you just did work. Because you moved the box, your force was upward, and it moved upward. So whatever force you applied, times the height that you lifted it, in Michael's case, it'd be about 3 feet or so. In Kendall's height, it would be, anyway, you just did work. But then you begin to walk. In what direction are your arms exerting force? Still upward, correct? Because if they didn't, box goes down and it's a bad day. Cans everywhere, juices flowing out of the can of beans into the carpet, it begins to reek. Okay, whatever, that would be a bad day. Which direction is the box moving though as you walk with it? Box is moving forward. That's perpendicular. They have nothing in common, do they? Your arms are doing no work. They're getting tired, but they're not doing any work by definition of physics. Does that make sense? So if upward motion, or downward motion, I suppose, is perpendicular to displacement, there is no work being done. Not by your arms. Now your legs are though, correct? Your feet are pushing backward, friction is pushing forward, so you are still doing work. It's just not your arms. Even though your arms are what are getting tired, your arms are not doing the work anymore. Does that make sense? That's one implication. Second implication, if you lower an object, you are doing negative work. If you lower an object, you are doing negative work. Think about this. If you're lowering something, for instance, we pick up a box and we go to set it on the floor, right? As we lower the object, what direction is our force? We're lowering the box. What direction is our force? Upward. We're not throwing the box down. That would be downward force. Even dropping the box would allow gravity to do the work, correct? We are lowering the box, but our force is still upward, correct? Because you're keeping it from crashing. But if the displacement is downward, they are acting in opposite directions. One of them has to be negative, because these are both vectors. Work happens to come out negative, even though work is a scalar. Negative work is being done. So, for instance, when you help your parents get Christmas decorations down out of the attic, and you hand that box of wreaths down to Mom. Well, be glad I didn't just drop it on you, Mom, but I'm doing negative work up here. So what you tired for? I don't get it. All right, if I am lifting weights, right? I'm lifting it upward, positive work. Downward, negative work. Positive work, negative work. Positive work, negative work. Set it back down. From a physics perspective, have I done any work at all? Because all the positive work I cancel by all the negative work. Your arms are very tired. Your body was worked out, yes, but from a physics perspective, no work has been done. Now again, that's not true with dissipative forces of dragging something horizontally. I push this way, it moves this way. That's work. I turn around, I push this way, it moves that way. That's positive work again. Okay? But whenever the work is opposite the motion, right? Whenever the force is in the opposite direction of motion, it comes out to negative work. Basically, think of it this way. Work is a transfer of energy, correct? If you just allowed the box to stay here, right? We understand, I don't want to get too far into this because it's the next chapter. With energy, we understand there's two types of energy, right? Potential and kinetic. Energy of motion is kinetic energy. Energy of position is potential. As an object sits up here, there's more potential to move. It just moved. It had kinetic. It is now sitting on the floor. It can't go anywhere now. It's already down on the floor level, correct? It now has no energy. It lost its energy. It doesn't even have potential energy down there anymore. When you lower an object, you are reducing its energy as you lower it. So literally, the work you are doing is taking energy out of that object. You are removing energy, hence negative work, if we want to think of it from that perspective as well. The final thing is a lot easier to understand. When concurrent forces act on an object, if concurrent forces act on an object, each force is doing work, assuming the object moves. Each force is doing work, assuming the object moves. Therefore, when there are multiple forces in play, the sum of individual work done equals total work. And that's kind of duh, but bears stating. The sum of individual work done equals total work done. So for instance, if all of us decided to, I don't know, we're all saying, okay, we're all going to carry one of these tables out here. So everybody gets behind and we all go to lift the table. Well, Kendall exerts a force that causes the table to go up. Kendall has done work. Audrey exerts a force that causes the table to go up. Audrey has done work. Michael does a force that causes the table to go up. Michael has done work. Everybody's done work. So what if we want to know how much total work was done? You had Kendall's work plus Audrey's work plus Michael's work. That's the total work. Duh. Right? And the reason behind that is we could add all your forces together, right? Because they're all concurrent forces. If they're all acting in the same direction, add them and then multiply by displacement. Distributive property of algebra says it's going to come out the same. So if individual forces are applied, you have, we have that done now. Let's take a look at some math problems. Let's take a look at some math problems. Now, page 171. Page 171 at the end of the chapter. And look at problem number 1. I'm going to read that for us, Michael.
A locomotive is pushing a 2.2 times 10 to the 5 negative Newton boxcar exactly 3.2 kilometers up a 30-degree slope at a constant speed of 15.6 meters per second. How much work is the locomotive doing? Ignore friction.
All right, so we have a slope. That's a pretty steep slope, too. We have a 30-degree slope, and that is the boxcar. Now, what does it tell me? It's a box, see? What does it tell me about the boxcar, class?
Exactly 3.2 kilometers.
It's a 3.2 kilometer boxcar? That's a long boxcar.
Displacement.
Okay, it tells me it's going to move at a displacement of 3.20, and it says kilometers. What does kilo mean? E3, right? So we say E3 meters. All right, so we know the displacement. So that's good. What else does it? What does it tell me about the boxcar though?
Oh. It's 2.2 times 10 to the fifth negative newton.
Well, that's a dash. For instance, if I say that Michael is a 200-pound boy, when you use it as an adjective, you put a hyphen in there. Going back to English class, sorry. That's all. That's just a hyphen to say that's how many Newton the boxcar is, since it was used as an adjective. So 2.2 E5 newtons. That's the weight of the boxcar. 2.2 E5 newtons. Now, if this somehow were lifting the boxcar 3.2 E3 meters, all right, maybe there were rockets underneath it, blast off, and it rises into the sky, 3.2. Okay, that's how much work the rockets did, okay, to lift it, I suppose. But it's not having to lift the boxcar, right? I mean, the ground is lifting it, it's just pushing it, correct? So this is not the force that we multiply by displacement. We have to figure out what force is applied by the locomotive. I don't know which force is applied. That's what causes the motion of 3.20 E3 meters. That's force times displacement gives us work. Make sense? But there's more than just weight and an applied force of the locomotive class. What other forces are in play?
Friction.
There would be some degree of frictional force unless it says to ignore friction.
Ignore it.
Oh boy, so we don't have to worry about friction, which means we don't have to worry about normal force. Now, technically there is a normal force. Technically there would be some degree of friction force, though again, admittedly, it's rolling metal on metal, rolling. So unless there's some friction on the squeaky wheels, which we all know they're squeaky wheels, we all were trained, okay? But we're going to ignore all of that, which means although there is a weight in the y, I don't really care about it. But I do care about weight in the x. This right here. And to find weight in the x, what part of the right triangle is the weight in the x, class? Remembering that this angle is also 30 degrees as this one is. We'd say weight in the x, class, is the opposite, and the true weight is the hypotenuse. So we could say we're going to use which trig function? Sine. So kato, we'll say that the sine of the 30-degree angle equals the opposite weight in the x over the hypotenuse, which is that 2.2 E5 newtons. And how much weight in the x is there?
1.1 E5 newtons.
Oh. Oh yeah. Sine of 30 is a half. It will come out evenly, right? Okay, so 1.1 E5 newtons. Now, it tells me one more number in the problem. It says that this boxcar is moving at a constant speed of 15.6 meters per second. Constant speed means
Cancellation.
no acceleration. Cancellation. That means what applied force must be exerted by the boxcar to push the or by the locomotive to push the boxcar.
1.1 E5 newtons.
Now, one would argue as well, the locomotive is also doing work to move itself up the hill, right? It has its own weight it is countering, but we're ignoring all of that. We're just focused on the work done to move the boxcar specifically, not to move the locomotive itself and the boxcar. So 1.185 newtons of applied force is pushing. That is going to be in the direction of motion because that's where the boxcar is going. So that's the applied force in the x, the 1.1 E5 newtons. And so to find work, class, we simply multiply force times displacement. Again, don't take the first force number given in the problem. Find what force is actually acting in the direction of motion as we did here. Multiply that by displacement, 1.1 E5 times 3.2 E3. And that's a lot of joules.
3.52
E8 joules. Remember, work measured in joules. And is it 3 sig? I think it is. 3.52 E8 joules of work done. Questions on this problem? I got a feel for how we're tying again those free body diagrams from chapter 9 into, well, we did it with springs and pendulums last time. Now we're moving it down into work problems. All right, take a look at number 3 and read that if you would, Kendall.
How much work is required to carry a 180 Newton stack of set up the third floor of an apartment building if the vertical distance between floors is 3.5 meters.
Alright, now, it's an apartment building. The ground floor is usually called what in an apartment building? First floor, right? That's usually first floor. Any of you have ever been to those apartment buildings? They have numbers like, it's like, 11, 12, 13, 14, and then it's 21, 22, 23, 24, and then 33, 31, 33. Usually it's first floor, second floor, third floor, right? So if you're going up to the third floor, how many flights of stairs? 2, right? Not 3. So that's the only tricky part. So if between the floors is 3.5 meters, you're carrying this thing. Now again, you are moving horizontally up the stairs as well, correct? Like as you step up, you're stepping forward, correct?
Mm-hmm.
But to lift this heavy sack, your motion, your force is exerted which direction? Upward, right? You happen to be moving forward, but to lift, that's upward motion. So I actually don't care about the forward motion. All I care about is the upward motion. And if between one floor and the next floor is 3.5 meters, then from ground floor to third floor class is a distance of 7 meters. So the displacement of lifting is a 7-meter displacement. How much force must be applied to carry this 180 Newton sack? It really is 180 newtons. If it weighs 180 newtons and it's not sitting on the floor anymore, you've got it. You had to exert a force of 180 newtons to get it up there. So the force you're applying is 180 newtons, and you're continuing to hold 180 newtons up as you go up the stairs and around and so forth. So how much work is done to carry this 180 Newton sack up 2 flights of stairs up a total vertical distance of 7 meters?
1,260.
And is it 3 sig figs or 2? 2. So we'll have to round it off and say 1,300 joules. Remember, SI is joules. What's the US again? Foot pounds. So joules and foot pounds. Questions on this? All right, at your seats, I want you to do number 2. Number 2 there at your seats. So number 2, calculate the work done in raising or lifting class.
480 newtons.
480 newtons would be the weight of the object. If you're lifting it, that means there must be an upward applied force of 480 newtons. Assuming you're lifting it at a constant speed, you're not trying to accelerate it faster and faster. So we'll assume a constant speed, bare minimum force, 480 newtons. It says to a height of 5.00 meters. Well, that height class, that's the displacement that the object was moved. And the 480 newtons, that's the applied force. So to find the work done class, just multiply and we end up with 2,400 joules. 2,400 joules of work done. 2 sig figs is sufficient. Then it says calculate the work done in raising 250 grams. Now, I don't want grams. Kilograms, but that's 0.250 kilograms. That is not the weight. What did it have to do? And so 0.25 times 9.8, what's the weight of this particular object?
2.45 newtons.
Only 2.45 newtons. So what is the applied force upward then? 2.45 newtons. And a distance of 215 centimeters. Well, 2.15 meters. And if you apply that force over that distance to find the work, you just multiply to get 5.2675, or rounded 2 sig figs, 5.3 joules of work done. All right, did we get both parts of number 2? All right, questions? Kendall got them, Michael got them, Audrey? Just some of the units perhaps? Or did you not find the weight?
No, I said 2.51.
Oh, 2.51, you're just dyslexic?
Mm-hmm.
All right, number 4 at your seats. Go to number 4 now. There at your seats. They're on page 171. Nice thing about raising, you don't have to worry about friction. Bad thing about sliding, friction. Did we get the free body diagram? As the box sits on the floor, it weighs 735 newtons, 735 newtons up, and 257.25 newtons of friction force ready to act. Until you match or eclipse 257.25 newtons, well, I guess technically that's kinetic friction force. It's slightly higher static friction force. But once you've got it moving, that's how much friction is resisting you. Well, that means bare minimum applied force class has got to be 257.25 newtons. So we're going to take that applied force times this displacement, and that's going to get the work done, which was, Audrey?
1,890.7.
Okay, and then round it off to 2 sig figs. 1,900 joules of work accomplished. Did you all get that as well? All right, any questions on work? All right, well, we do not have time to get into power, so we'll save power for after Thanksgiving vacation. Not going to give you any homework tonight, so you enjoy a little bit of a break there. Get some rest over Thanksgiving. Those watching, if this happens to be before Thanksgiving, you have a happy Thanksgiving and enjoy the time off, and then we'll be back in about a week and a half. And we'll see if you remember anything about work. See if you ever remember hearing about work, and we'll see what we remember. So we'll probably do a lot of review in the next lesson as well. All right, when the bell rings, you'll be dismissed.